So it's really nice to be here. So first of all, thanks to the organizers of this conference. I'm afraid that after 3 days of very dense presentations, you are a bit tired, but don't worry, because this presentation will be very short and it's less scientific than previous presentations and more on tools used for simulation. I think that a good starting point for this presentation could be a reference of a very recent research topic jointly published in Frontiers in Neuroscience and Frontiers in Neuroinformatics, titled Neuroscience, Computing Performance and Benchmarks, Why It Matters to Neuroscience How Fast We Can Compute. And if we look at the list of authors of this of the papers in this research topic, we can see that there are contributions from the community of users and developers of the most popular spiking neural network simulators, as Neuron, Ness, Brian, Jen, Anarchy, as well as contributions from the community of neuromorphic systems as Spinnaker, Spiky, and Brain Scales. Oops. In the past 2 decades, the developers of the 3 most popular spiking neural network simulators, CPU-based spiking neural network simulators, namely Neuron, Ness, and Brian, have given the highest priority to methodological rigor, and they have made a great effort to provide users with reliable tools, high-quality documentation, and with user-friendly interfaces. But today, this is not enough for the needs of the neuroscience community, which is pressing for increasingly higher performance and for the possibility of simulating larger models, larger and more complex models. So in recent years, the developers are also making a great effort to improve performance, particularly for large-scale and very large-scale models. Indeed, many users are working on models that depends on a certain number of free parameters, and the values of those parameters often have to be optimized in such a way that the model behavior is as close as possible to experimental observations. Also in biologically inspired artificial intelligence models, the parameters often have to be optimized to maximize some figure of merits. And the exploration of the free parameter space often require a huge number of simulations. So it's very important to reduce the simulation time. Also, users seeking to investigate the relationship between high-level cognitive functions and low-level neuronal signals need to simulate large models over relatively long biological time. And indeed, high-level cognitive processes are the result of collective behavior of very large populations of neurons interconnected. and their simulation can be a very challenging task. And also there's a growing interest in integrated models, bringing together different areas of the brain involved in different functions as learning, working memory, long-term memory, vision, motor actions. And the simulation of such complex and large models require adequate hardware and software solutions. Basically, we can distinguish three kind of approaches. We have CPU-based simulators, which CPU-based simulations, which can go from multi-core CPU workstations to multi-core CPU clusters. Then we have GPU-based simulations, which can be performed on a single GPU device or on multi-GPU systems with 2 or more GPU devices in a single machine connected to each other by fast PCI Express or NVLink buses, or on GPU clusters. And then last but not least, we have neuromorphic systems, which can be digital as a spinnaker or analog as a spike and brain scales. In general, I think that none of these approaches can be considered absolutely better than the others. And all three have their reasons for being supported and for being developed. In principle, neuromorphic systems can offer huge advantages in terms of speed and energy consumption. However, they lack the flexibility of CPU and GPU-based approaches, and the number of neuron and synapse models that they can simulate is always relatively small. About the CPU versus GPU approaches, we should observe that the three most popular CPU-based spiking neural network simulators, Nest, Neuron, and Brian, are all three going in the direction of integrating CPU and GPU-based approaches. Nest with a Nest GPU, and Neuron with Core Neuron, and Brian with Brian 2 CUDA and with Brian 2 Gen. And also, this integration between CPU and GPU approaches was already present in some other popular simulators as CarSim and Anarchy. I think that having different simulators and different approaches is a good thing, and that it can have beneficial consequences because it is a stimulus for the improvement of all simulators. Here you can see on the top NVIDIA A100 GPU chip, and below the Ampere, the NVIDIA Ampere architecture on which this chip is based. The base element of all NVIDIA GPU architectures is the so-called streaming multiprocessor, or SM. Here you can see the streaming multiprocessor of the Ampere architecture, which is composed by 4 compute engines called streaming processors. Each of them has a certain number of compute elements which can process different type of data. More specifically, in each streaming processor, we have 16 computing elements for processing 32-bit integers, 16 single precision 32-bit floating point units, and 8 double precision 64-bit compute elements. And finally, 1 tensor core unit for performing operation with matrix and tensors. The 800 chip has 128 streaming multiprocessors in total. However, only 108 of them are actually used, just to give some margin for production defects. And with those 108 streaming multiprocessor, this chip has a total of about 7,000 compute elements for integers, 7,000 compute elements for single precision floating point operation, 3,500 compute elements for double precision floating point operation, and about 400 tensor core units. Those are huge numbers. However, the actual throughput does not depend only on the number of compute elements, because it's strongly limited by the high latency of access to the global memory, which is relatively slow, and also on the much smaller latency of arithmetic pipelines. To reduce the latencies of memory access, there are different levels of cache memory, which are separate for instructions and for data. The successor of the 800 chip is the H100 chip, which is based on the Hopper architecture, which has more than twice the compute elements of the 800, a memory bandwidth which is about 50% higher, and 8 gigabytes of GPU memory. So these are great news for GPU developers and users. Okay, the real problem is that the price is still very high. It's about 30,000 euros per chip. Now about software. CUDA is a parallel computing platform with a language similar to C and C++, which has been developed by NVIDIA to allow software developers to take full advantage of the GPU capabilities. From a software perspective, we need to keep in mind that basically GPUs are SIMD devices, where SIMD is an acronym that means single instruction, multiple data. GPU threads are organized in groups that are in groups of 32 threads each, which are called warps. And the GPUs work more efficiently if all threads in a warp execute the same instructions. Branching is allowed. However, if a thread executes a branch, all the other threads of the same warp have to wait until the branch is complete. So branching should be limited as much as possible. And also access to global memory should be limited as much as possible because they are slow. In many cases, it can be useful to use shared memory, which is much smaller than the global memory, but has a much lower latency for the access. So the message is that in order to have a full advantage from the high degree of parallelism of GPUs, the software must be carefully designed, having really in mind how the GPUs work. It's not as simple as, okay, since the language is very similar to C and C++, I can just take a program that was designed for the CPU and I run it on the GPU. It's not so simple, unfortunately. But if the software is designed properly, there can be huge advantages from this high degree of parallelism. So now something about Nest GPU. Nest GPU is a GPU MPI library for fast simulation of spiking neuronal networks, which was recently included in the Nest initiative with the aim of integrating it with Nest, with a Nest simulator, to expand it and to give it the possibility of simulations on GPU hardware. Nest GPU represents the development of a library that was previously called Neuron GPU. And about 1 year ago, the Nest Initiative board approved the inclusion of this library in the Nest Initiative. And this integration gave a significant boost to the development of this library. And now many people are contributing to its development. In particular, Johanna Senk, Jose Villamar, Gianmarco Tidia, and Elena Pastorelli are those more involved in maintaining this library in the GitHub repository, improving the code, solving issues, integrating Nest GPU with the other Nest tools, and so on. Pooja Babu and Charles Linson are developing the NestML extension to allow users to easily build new neural models. Gianmarco Tidia and Jessica Mitchell are working on the documentation, and the Ape Lab of the ENFN, in particular Pier Stanislao Paolucci, Francesco Simula, Elena Pastorelli, Leonardo Tonielli, Chiara De Luca, are contributing both in the development of MPI algorithm for for remote spike communications, and to the validation of the software on different types of models, among which the TACO model, the multi-area model, the mouse hemisphere models, the Potian-Disman model. Sasha Van Albada, Jasper Albert, and Jari Pronold contributed with the validation of the of Nest GPU on the multi-area model just presented by Sasha in the previous presentation, and to the comparison of Nest GPU with Nest. Hans Eckhard Plesser and Tanguy Fardet contributed in the development of the multi-synapse ADEX model, which is the basis of all multi-synapse and in the future multi-compartment model. Marcus Diesman, Pier Stanislao Paolucci, and Abigail Morrison are contributing in finding the human and computing resources necessary to carry out this project. This Nest GPU, this is the Nest GPU data sheet. The base installation of Nest GPU comes with simple leaking integrated file neural models, Izikevich models, different multi-synapse ADEX models with current or conductance-based synapses. As I said before, new models can be generated with NestML. Different devices can be simulated, and also devices for measuring the spike frequency or state variables and parameters. It is possible to use fifth order Runge-Kutta method for the solution of the differential equations of the dynamics. Concerning plasticity, the current version of Nest GPU can only simulate STDP synapses with nearest neighbor spike interaction. However, we plan to implement new types of plasticity in the near future. The Python interface is very similar to Nest in the main commands, use of dictionaries, connection rules, devices, and neural models names and parameters. If you look at this script, you can immediately see how similar it is to Nest. Okay, as a benchmark for evaluating the performance of a Nest GPU, I want to present here first the results on the Portian-Diesman cortical microcircuit model, which has been already described in previous presentations. Here you can see the comparison between Nest GPU and GEN, which is another popular GPU-based spike neural network simulator. The initialization time of Nest GPU, of the current version of Nest GPU, is similar to that of Nest. This is because at the moment the connections are, yes, I'm close to the end. The connections are generated first in the RAM, and only at the end of the initialization, just before the simulation, they are copied from the RAM to the GPU memory. However, very recently, we implemented a first prototype of an approach for generating the connections directly in the GPU memory in parallel. And with this approach, the initialization time is much, much faster by 2 orders of magnitude, being for this model less than 0.5 seconds. Concerning the simulation time on a V100 GPU, we can simulate the full Portian-Diesman cortical microcircuit model in I don't see the number, but I think it was 1.6 seconds per second of biological activity. On a RTX 2080 Ti GPU, the simulation time is as small as 1.05 seconds per second of biological activity. Those are the results from this publication, but very recently we made several improvements to the code, and now the simulation time is smaller than real time. So we can simulate the model in 0.97 seconds per second of biological activity. Finally, as a benchmark for the MPI GPU simulation, we used the multi-area model presented by Sasha Van Albada in the previous very nice presentation. In this case, the initialization time for Nest GPU is much larger than NAST, but we plan to improve it. I will say you how. While for the state propagation simulation, for the ground state, Nest GPU can simulate 1 second of biological activity in 6.5 seconds, while the metastable state can be simulated in about 15 seconds per second of biological activity, against about 48 seconds for Nest. Sorry, I was in hurry. I forgot to say that those simulations were made on 2 HPC clusters. Nest GPU simulation have been performed on the use of HPC cluster using 32 compute nodes, each equipped with an NVIDIA V100 GPU, while the Nest simulation have been performed on the Eureka DC HPC cluster on 32 compute nodes, each with 2 AMD EPIC CPUs with 2 times 64 cores per node. Just to conclude, some final consideration. We can significantly improve the initialization time by exploiting the fact that actually each MPI process has all the information that it needs to generate the connections without exchanging MPI packets with the other MPI process. Basically, they can generate the connection without speaking to each other, because they have all the knowledge to do it if they start from the same random numbers. So in this way, we can significantly reduce the initialization time. While concerning the simulation time on MPI GPU cluster, we can exploit the fact that there are physical limitations to the speed of the transfer of spikes among nodes. So we can use the delays to pack the spikes and send them less frequently. So not every time step of the simulation, but every a certain number of time steps depending on the delay. And in this way, we can significantly reduce the time, the fraction of the simulation time used for the spike communication, which is the main bottleneck in those simulations. And finally, clearly, we can have huge advantages by using GPU devices of the newest generation. The results that I have shown previously have been obtained on a GPU cluster with V100 GPUs, but I have to say that the V100 is already a relatively old GPU devices, because as I have shown in a previous slide, it has been passed already by 2 new generations of GPU devices. And also, for a GPU cluster, having only 1 GPU device per node is not the optimal configuration. It would be better to have more GPU devices per node to reduce the communication time. At least 4 GPU devices per node, I would say. So we could have significant improvement just by running the model on clusters with more GPU devices per node and with newest generation devices. Thank you for your attention.